have you ever heard of the phrase, perfection is not attainable? Well, in quantum physics, this saying's true when it comes to uncertainty in measurements. And uncertainty is basically just how unsure we are about the accuracy of our measurement. And usually, we can decrease the uncertainty or eliminate it by using more accurate equipment or improving our method of measurement. But what if there was a situation where the uncertainty could not be eliminated, and no matter how hard we tried or how accurate our equipment was, there was no way in which we could measure certain values exactly? Well, there is, in the quantum world. The uncertainty principle asserts a fundamental limit to the accuracy with which we can measure certain physical quantities of a quantum object. For example, it's impossible for us to measure the exact position and the exact momentum of an electron at the same time. The uncertainty principle exists because of a feature of quantum particles called wave-particle duality. A particle can only have one position at a specific instant in time. Like if you throw a ball at a group of people, the ball hits only one person, and not the whole group at once. But if you blow a trumpet next to that same group, the sound waves spread around and are heard by the whole group. So quantum particles are said to act both as a particle and a wave, where the particle is most likely to be found in the places where the oscillations of the wave are the most intense. To explain why the uncertainty principle exists, let's borrow a quantum particle, an electron for example. This electron has a probability wave associated with it, which tells us where we're most likely to find it, but also allows us to know its momentum. But if we want to narrow down the probability and find the exact position of the electron, we can do this using something called a wave packet. It's made by combining many waves of different wavelengths, giving us an interference pattern, a higher probability of the electron being in some places and zero probability in others. Eventually, we end up with something like this. And if we kept bringing more wavelengths into our wave packet, we can actually have close to 100% certainty as to our electron's position. Great, right? Unfortunately, knowing so much about a quantum particle comes with a price, because even though we now have a clear idea of where our electron is, we've lost all accurate knowledge of its momentum. Remember all those different wavelengths we used to build our wave packet? Different wavelength equals different momentum, so realistically, our electron could have any one of those momentums. Unless we take apart our wave packet and decrease the number of waves until we're back to a single probability wave with a definite wavelength and a definite momentum. And if we did that, we'd finally know the exact momentum of our electron. But you guessed it, we've lost all certainty of its position. You see, to get a quite accurate measurement about one quantity, we had to sacrifice our certainty about the other. This is the Heisenberg Uncertainty Principle, and it shows us that there's an inevitable amount of mystery in nature, because even though we'd all love to believe that science has unlocked everything there is to know about the quantum world, there are still countless secrets out there, just waiting to be uncovered.